Last time we went over how to get the incident radiation on a tilted surface. Really quickly, a couple things about that before we move on to the next topic, and that is a fourth method of collecting solar energy. So on a tilted surface, again, what we said is that there's going to be some direct radiation coming directly from the sun. There'll be diffuse coming from the sky dome that's hitting there. And then the ground at front, there might be some reflected that comes and hits that surface. And so we need to figure out all three in order to determine the total incident radiation, say in watts per meter squared or BTH per square foot on that surface. Just a quick reminder, a little more thought on that. Doing that involved figuring out radiation view factors, and the common symbol for the radiation view factor is Fij. Fij would stand for the fraction of radiation leaving surface I that hits or reaches surface J. And really as I've been talking to a couple students, I've been saying, look, when you think about it, the math in this class is really not that difficult. Really what the challenge is understanding what these terms mean. So I really encourage you when you're working problems, if you look at every single term in a formula, what does that term mean? So I just want to do a little bit of practice with that, hopefully get you guys a little bit more secure on that. So in this case here, let's imagine that we have a sphere within a sphere and just do that classic problem where we figure out the radiation view factors. So 2 is going to be the outer hollow sphere, and then 1 is going to be this inner sphere. And both are radiating. So I'm going to say, like, just this point right here, both are radiating diffusely. 1 is radiating in all directions at every single point on that sphere. Same thing with 2. If I go to every single point on the inner surface of the sphere, it is radiating all directions, okay? And it turns out with just a little bit of analytical work, you can figure out those fractions. We can figure out the fraction leaving 1 that hits 2 and the fraction leaving 2 that hits 1. And you may even have it in your mind, but to give you a little practice, what I want you to do is just quickly, you could write this down or at least just think your way through it. Pick quickly for each of the following 4, come up with what you think the value should be: 0, small, large, or 1. And bear with me while I get them up on the board, and then I encourage you to pause the video. Okay, so all we're doing for now is figuring out those 4: F12, F11, F21, and whoops, mistake there, apologize for that, F22. So figuring out those 4 radiation view factors for this case. Encourage you to pause the video and I'll get the answers up there in just a second. All right, well, let's start with the easy one, F12. That would be this fraction of this radiation that leaves and actually hits 2. And we've got to consider every little bit of radiation that leaves 1, how much of it actually reaches or hits 2. In addition, we have to do every single point on that surface, which seems, like a lot of work. But just quickly, if you go to a couple points and think about it, hopefully you can see that F12 is equal to 1. Every little bit of radiation that leaves 1 ends up hitting surface 2. All right, let's do the next easiest one. Let's do F11, okay? F11. How much of this radiation that leaves surface 1 actually is going to hit surface 1? And so if you can remember that radiation basically travels in a straight line path, it doesn't make a 180 and come back, hopefully it makes sense to you that every single bit of radiation leaving surface 1 is going to hit surface 2. None of it is going to end up hitting surface 1, so that's going to be equal to 0. All right. Hopefully, if you take a look, this makes sense. This is saying all the radiation from surface 1 hits surface 2. None of it hits surface 1. And, of course, that is a very reasonable thing. So that does it for 1. Let's see what you got for 2. Okay. So F21, we would take some sort of point like this and draw some radiation and see if it's going to hit surface 1. So that one's going to hit surface 1. That one there might skim it and hit it over there like that. But if I draw this one here like this, and I'll just do it as a straight arrow instead of a squiggly line, clearly that's going to miss it. So there's no way F21 is going to be equal to 1, okay? but it's also not going to be equal to 0. Well, you can go through the math. It turns out, in this case, this will be probably less than 50%. This over here is going to hit 2. That's going to hit 2. That's going to hit 2. That's going to hit 1. That's going to hit 1. That's going to hit 2. That's going to hit 2. And hopefully it makes sense that it's going to be less than 50%. There's a way to calculate it. Let's just say it turns out to be 0.3. All right. Well, F22, is that going to be 0, 1, or some sort of number in between? Well, like I was saying, it looks like most of it is that comes off 2 is going to miss 1 and then come over and end up hitting 2, hitting 2, hitting 2, hitting 2. So this number here is going to be relatively large. And logically, if you think about it, then it has to be 0.7. All right, so that's a little bit of review of Fij, and before we go on to really quickly, a quick note on the equations that we did last time. Probably the main one that we have in that equation is FCS, and that is the fraction of the radiation leaving the collector that ends up hitting the sky. Okay, more on that in just a minute. All right, so practicing that idea of, focusing on the meaning of terms, I would encourage you to give yourself a quick quiz. So either pause the video or even write down these two equations, which are equations essentially that you've seen before, and try to go term by term and figure out what those are. So again, take a second, pause the video. This will be good for your understanding of solar. All right, so hopefully you've gone over that. So these equations, sometimes I've done it as G sub T or G theta. This would stand for the total irradiation on a collector surface or on a surface like a window that could be tilted. So ordinarily we just call it G because it's not the horizontal, it's not the vertical, etc. So thinking conceptually how we get that? Well, here is a very, very crude picture. There's south. There's a collector that's actually not oriented towards south. And we're going to get 3 types of radiation on it. We're going to get the direct that comes from the sun. We're going to get the diffuse that comes from the sky. Okay, and finally, we are going to get stuff that comes off the ground, and some of that stuff coming off the ground is going to hit the collector. We have to figure out each of those, the direct, the diffuse, and the ground reflected, or there might be other reflections in order to get the total. So that's what we got here. We've got the direct, we've got the diffuse, okay, and we have the ground reflected for that last term. So let's go term by term and make sure we got it. This is the normal direct, and we multiply it by the cosine of the angle of incidence. That's old news. This was new news last lecture, and we're going to take the diffuse on the horizontal and multiply by FCS, which stands for the fraction of radiation leaving the collector that hits the sky. All right, some intuition about FCS, the fraction leaving the collector that hits the sky. So if that red thing represents the collector, not 100% of the radiation coming off this collector here is going to hit the sky. Some's going to hit the ground. In this particular case, we can think of FCS. FCS is standing for the fraction of the sky the collector is exposed to. And it is exposed to this stuff over here, but not that stuff over there. And so the greater we make beta, the tilt of the collector, the less of the sky is exposed to. All right, how about that last term, FCS rho G GHI? Well, GHI is the total incident on the ground, and rho G would be the reflectance of the ground. So this represents, this combination right here, that portion right there, represents how much is coming off the ground. FCG, I'd like you to be able to put it in words. That's the fraction leaving the collector that hits the ground. So let's go ahead and take a look at that term right there. Is it 1? Does all this radiation leaving the collector hit the ground, or is it 0? Well, hopefully you can look at it and say it's somewhere in between. Some of the radiation of this that's leaving this is going to actually hit the ground, and some is going to actually end up hitting the sky. So it's somewhere between 0 and 1. We gave you the formula for that last time. The reason this formula works out takes a little bit of explanation. And for those of you who are in ME 126, you'll go over the reciprocity theorem, and then once you understand the reciprocity theorem, you can very easily show that that makes sense. In this class, we're just going to use it. All right, what's the difference between the top equation and the second equation? Well, G is per second, okay, and I is per hour, energy incident per hour. And so in a sense, what you're really doing more when you do modeling, say like in Excel, is you're using this version, okay? You are doing work per hour, okay? Please don't stress about that too much, but at least try to think about it. A lot of times the data we have is essentially a rate that we assume to be holding over an hour, and all this math ends up being the same. The one thing that's a little bit tricky over the course of the hour is that the angle of incidence changes. But if we get the angle of incidence at the hour midpoint, that will work. Okay, well, the next thing I want to do with you guys is get going on the next option for collecting solar. So here are our options really quickly. And so our first thing is just to build a black box, or build a box and make the top black. So, and fill it with water, all right? All the calculations we did so far assume that the top of the water was horizontal, top of the box was horizontal, so the solar was coming in and hitting this surface here like that. Now you guys know enough math that you can take the calculations we did earlier, tilt this up so it more directly faces the sun, and you have a smaller angle of incidence, and we're going to do a lot better. How well are we going to do efficiency-wise? Well, it really depends in part on how deep you make this box. And that's kind of an interesting calculation to go through. We optimistically got somewhere around 50% in some of the Excel work we did earlier in the semester. And that is within the realm of possibility, but there are some shortcomings. Okay, second option, all right, is to take a resistor and put it in water. So this was a resistor, you put it in some water, and then you take this resistor and you run wires back to a PV panel. And you take the PV panel, takes that energy from the sun, and it makes it into electrical energy, which travels through the wire, and then the resistor changes it into thermal energy. Okay, that was lousy. That efficiency was lousy. And the reason it's lousy is the PV panel is really poor at converting solar energy into electrical energy. All right. The third option was to skip the resistor and instead take the wire and hook it up to a heat pump, which grabs free heat from the air. All right, so those were, that efficiency was a little bit better. Between the three, the batch collector, the heat pump, and the resistor, I never, ever, hardly ever see the resistor being done. The heat pump is done a lot. That's something that the Energy Commission is really promoting. The batch collector, that's right now a little bit more the province of do-it-yourselfers, etc. But there are companies out there that sell batch collectors, and there are people who are huge fans of them with proper use can way outperform a heat pump. But nonetheless, there is another option out there, which is a lot better. And to get at that, I would like to take a second and show you what is a problem with the batch collector. All right, so batch collector. Rough drawing of what we got. We've got this box right here, okay? And now we're going to, if you went through and did the calculations, you would tilt it up. It's some sort of tilt beta so that we get a small angle of incidence. In other words, so that the beam radiation pretty much comes in. All right, so just very briefly, some problems with it. First of all, it turns out that what we want to do is we want the surface area to be large, and so we don't want this to be very deep. So if we're trying to get 40 gallons of water heated up for our family, it's going to take a pretty large batch collector in order to get good efficiency. Okay, second problem, what if we want to, store some water overnight? Well, during the nighttime, this thing is going to radiate out, okay? That's emission, all right? And in fact, it emits all day long, but at night, that emission is going to lead to a pretty dramatic drop in temperature. So that's not very good, how to handle that at night. Certainly there are people who just say, look, I'm going to do my showering, I'm going to do my dishwashing, I'm going to do everything like that around 5:30 to 6 o'clock when that thing's hottest. And that's good enough. But again, might be nice to have some hot water in the morning. That's a downside. Okay, so final problem has to do with the actual heat transfer of collection. So what we did earlier when we did this calculations is we assumed that the energy that gets into the top plate there gets into the water. So let's say like 400 BTUs per minute is getting into that hot plate, top plate. 400 BTUs per minute is getting into that water. And there's an issue with that. So what I would like to do, this rectangle here represents the top surface that faces the sun. And we could say that this plate has two important surfaces actually. It has this side here, that it has this side right here that faces the sun, and it has this side here that faces the water. So I would like you just to do arrows for the top, in or out, and think about your different processes. So our processes were convection, emission, irradiation, absorption. See if we can work those out. So I'll be doing it myself. Arrows just into or out of the top. Let's see how those end up turning out. Okay, so there's the top, and you should have a total of 3. Okay, this one right here, sorry about that pen, I should change that pen, is the stuff that's being absorbed. Okay, the solar that's being absorbed, and one of these would be convection, likely, and one of them would be emission. Okay, and so to get how much is actually going in, we would take this minus this minus this. So just making up some numbers to try to make sense of it. Let's say that we're absorbing 400 watts per meter squared. That would be fantastic. Okay, and we're emitting 100 and we're losing 100 by convection. Then we would have 200 watts per meter squared going into this top. Okay, how about on this side over here? What's going on with that? Well, I'd like you to go ahead and do the interactions on this bottom surface here and see how many arrows you get. Go ahead and pause and think for a second. Well, ordinarily it would just be 1. We're hoping this plate is getting hot and energy is going out of that plate and into the water. What form of heat transfer is that? And that's going to be convection. Okay. So we would like that to be, if I have those numbers, in those numbers I have there, we would like that to be 200. Okay, the amount that goes into the top is equal to the amount that goes into the water. Okay, how about an equation for that heat transfer? So our basic heat transfer, convective heat transfer equation is we take the difference between the surface temperature, okay, and I could call that TSB for the surface temperature of the bottom, minus the temperature of the water, and I'm missing one term in that equation, and that is the convective heat transfer coefficient. All right, so what I'd like you to think about it, for those of you, all of you have either are in heat transfer or have taken heat transfer, what's H going to be like in this case, good or bad? And the answer is going to be really, really poor because H, the heat transfer coefficient depends on how much water movement. In this batch collector, we have hardly any water movement. So this is going to be poor. As a consequence, this number right here is often going to be less than 200. So the amount that actually gets into the surface and the amount that gets into the water is going to be they're going to differ. I'm just going to call it 150 to get a number there. And if that were the case, what we would have is a net of 50 going into this plate. What's going to happen to the plate? It's going to warm up. This top plate's going to warm. That top plate's going to warm up. What's going to happen to emission and convection? Emission and convection are going to increase. So we need some way to get this water out of the heat out of the plate and into the water. So one thing you could imagine doing, and some people do this actually, it's kind of interesting, is put some sort of stir inside the batch collector. And that'll keep that water moving around and stirring and picking up that heat more effectively. That is a great alternative. But there is another alternative that seems to have worked out over time to be the next solution. And let's take a look at that. All right, well, here's the solution, okay? What you do is, to get movement, is you get a pump. Doesn't have to be a pump. There are some alternatives, but that's gonna be our primary option. And it's gonna move the water through a tube. That tube is collected to fins that are on either side, and those fins are exposed to the sun. So some virtues that you get that you get with this. First of all, you get the fluid moving. As a consequence of the fluid moving, you avoid that stagnant situation where you have a low H, you have a better H. Secondly, once the hot water comes out there, you have it go back to your tank, and that tank can be inside. Then you don't have the problem with the batch collector has, namely that you have a bunch of water sitting outside. Maybe you have to come cover the batch collector at night, or you have to like put an insulating surface over it. No, you don't have to do this because all of this tank can be inside, and it works out really, really well. This is sort of a theoretical drawing. Let's take a look at the real thing. All right, so this is the basic alternative that we have down here. In short, what we're trying to do is create a flow-through system so we get good heat transfer between our collection surface and our fluid, which in this case is going to be water. So just a little bit about the gross overall anatomy. This line down right here would probably be from our tank or from our pump. And then if you look down here, you should see a large pipe going across, and that is a main pipe. And then you have these splitter small pipes that go up. You can't actually see the pipes all that well, but you can see the bumps going up and actually coming to this pipe over here. I have this pipe crudely plugged over here like this, and so the water would come in an outlet. And over here, then the water would head back to the tank. Again, hopefully as we're going through, we're going to get some pretty good heat transfer from the warm plate to the water. It's not going to work that well today, so just really quickly, maybe if you just try to visualize for yourself for the angle of incidence. So I'll give you a second to think about that. You might want to pause. Hey, what's the angle of incidence right now? And just giving you a general on that, towards you guys, that's south. So I've got the azimuth of the south. Someone might say, well, wait a minute, this collector is facing up. That's the normal line. But it is the direction the collector is tilted towards, and this is tilted towards the sun, towards the south, so it's azimuth to south. Okay, the sun actually is coming from over about here like this, so we have a pretty small angle of incidence. Another way of putting that, the sun is almost going directly into the collector. You would think it'd be pretty good, but if you take up a look at the sky, there's a fair amount of cloud cover up there, and so we don't have very much direct radiation. It's mostly diffuse and a little bit of ground reflected, so not that good. But let's just verify that it's working some. So if the camera person, if you would come on up, and we'll get a close-up down here of this area right here like this. So once again, this is the inlet manifold, about 3/4 inch pipe, and then we have these 3/8 inch pipes coming up. This is the fin plate essentially that means is allowing us to have a lot of surface area. And even though it's not that warm outside and it's not that sunny, I believe we're getting some temperature here. So let's take a look at what it looks like. So I'm using this right here, and this is actually taking the temperature of the manifold pipe. It's like 85-ish. That outer edge is about 80, but about 85-ish. Okay, and if I move up, now I'm pointing at the fin itself, and I've got 93, so that looks pretty good. So this should be able to warm up water somewhat, but not great. On a really sunny day, this surface up here could get to 140. Okay, how about the coating of the surface? Well, it's black, and obviously that's going to be good for solar absorption. But there's something else about it that's really important. So let me see if I get that temperature again. So 81, 82. I think some of what's going on is I've been shading it a little bit. Okay, so back to the pipe here. Yeah, there's that 86. Okay, and there we go, 91. And then as I move up, in this region here, the paint is worn off. But as I move up, I get the surfaces around 38 degrees or 37 degrees. And if I touch this, I mean, this is warm. This is warm enough that I don't want to keep my hand there for a substantial period of time. And yet it's reading like 38 degrees. So what's going on with that? If just as a quick reminder, there's two main radiation properties of surfaces that we want to be. So again, there's two main radiation properties of the surface that we want to be really good at understanding. One is the absorptivity and one is the emissivity. This surface has a high absorptivity, perfect for solar, and it has an unusual property, corresponding property of low emissivity. This measurement device takes in a certain amount of radiation and has an assumed emissivity. And as a consequence, there's low radiation coming off this, and then when it goes through and uses this assumed emissivity to calculate the temperature, it gets that there's a really low temperature. So once again, this is a really nice surface, high absorptivity, low emissivity, and let's just get it going and see how it actually works. Okay, so we got it up and running. If you look down at that end, the water's coming into the main pipe. It's going up these riser pipes, collecting in this top pipe right over here and coming out. It's actually, the inlet water is about 60 degrees, and so this is coming out about 71, 72. We don't need to look at it, but if I use this thermometer to verify, I'm getting about a 10, 11, 12 degree rise as we're going through, and we're collecting that hot water in the bucket. Obviously, if it was a sunnier day, hopefully we'd be coming about 90. And then really what we do ideally, if we wanted to get really warm water, is we would have this water recirculate around as many times as necessary to get it up to the temperature that we want. So what we saw is just called the flat plate collector solution. So even though the collector plate has little ridges, basically it's pretty much flat. You have inlet water, you have outlet water, and the water comes out warm. And we were talking about efficiency earlier, and that is a primary question here. What is the efficiency of this type of system? So the efficiency is a rate of, gives us a measure of how well we're doing at collecting solar. So it would be a ratio of, in the denominator, we're going to have how much incident solar there is in, say, BTUs per hour or BTUs per minute. And then we're going to, in the numerator, have the collection, which is sometimes in many textbooks, including the one in this class, is termed Q useful. All right, and in this particular case, we can say that the incident solar is going to be the G. Okay, you could put a subscript T if it's a tilted surface, or theta. Sorry about that. G, subscript T or subscript theta. And that would be, say, in BTH per foot squared. And then we're going to multiply it by the area of our collector surface, the area of this collector surface right here. And then how are we going to calculate Q useful? Well, for starters, what is going on physically with Q useful, if we have to describe it in words, and that is energies going into the water. So basically what we're going to do is we're going to, pardon me, sorry about that. We're going to here have energy or rate that energy goes to the H2O. And that's the starting point. I'm going to give you a little bit more refined formula, but let's just take an example where you guys go ahead and work that out. So let's just go ahead and say we've got really good solar. That was not good solar outside this afternoon, but let's just say that there was 250 BTH per foot squared. Okay, and in addition, let's just say that the area of the collector is 30 square feet, which is about what I had out there, 30 square feet. Okay, and let's say we were able to do some measurements and figure out the rate at which the water picked up energy. So we're going to say that the water rate is a typical number, let's say 40 BTUs per minute. All right, so just to make sure on track with just this really basic definition of efficiency, why don't you go ahead and calculate the efficiency in that situation, and I'll be doing it myself. Okay, first step. In the denominator, I want to get the rate that solar is coming in. How good are we, how much solar is actually coming in? And so the way to get that is to get the rate that solar is coming in per unit area multiplied by the area. So I did 250 times 30, but for reasons that you'll see or perhaps already see, it'd be nice to have it in BTUs per minute. So I divided, and we have 125 BTUs per minute. So hitting this collector every minute is the energy of 125 matches. How did we do as far as collecting it? We got 40 of it into the water. The rest actually of that energy went elsewhere. Still not bad. So 40 BTUs per minute. Okay. And then as usual for efficiency, if we've done our calculations correctly, our computations correctly, we get a unitless number. okay? And I got an efficiency of 32%. All right, not great, but nonetheless a lot better than PV. PV is not nearly going to do that well, and perhaps we can make it better. All right. How would you go about then testing a collector? And that's a huge deal. Actually, there are jobs out there where collectors need to be certified to have certain efficiency levels. You have to be, if you claim that your collector has a certain efficiency according to a certain test protocol, you need to actually have that completed by someone, and that is. There are engineers that work on that sort of thing. Well, what you would do then is you would, thinking about this calculation over here, what you would need you would need G. Well, you can get that starting with data such as GHI, and then doing all the sort of calculations that we have done this semester in order to get G. Area, obviously, you could just measure. And how about energy into water? Well, that goes back to one of your most basic calculations in mechanical engineering related to heat and fluids and other things like that. So just let me get that back up there to remind you what's going on. Okay, so what this is supposed to represent is fluid going into a pipe and then coming out of pipe. And what rate does it end up picking up heat? Well, what you would do basically is you would measure the inlet temperature, which we could call Tn, and the outlet temperature, which we would call T out. And the heat gained is going to be proportional to how much the energy actually rises. Temperature actually rises. By the way, of course, with this calculation, or this formula I'm about to give you, we're assuming that there's no phase change. The only thing that happens to the fluid is temperature change, which is the usual case for solar systems. Okay, so basically, you've seen various versions of this formula before. The rate that heat goes to a fluid as it flows through some device, either into the fluid or out of the fluid, you take the specific heat of the fluid, and you multiply it by the change in temperature, which we could do as T out minus T in. Again, I'm sorry about that. Pardon me. Sorry, let's get a little bit off the screen. Okay, and then what we're going to end up doing, pardon me. Good. Okay, is multiply by the fluid mass flow rate. And in various classes that you've taken, you've seen that relationship. But of course, that can apply to this particular situation. So that's easy enough to do. If you were testing, you could have a thermometer that would measure the inlet temperature to your water. Outside, when we were working, that was about 60-degree water. You could have the outlet temperature, and I was getting to about 72 degrees water. And then if you could get the mass flow rate, then you could work out the energy to the water. Now, it doesn't necessarily be to water. In many solar systems, there is some sort of antifreeze in this fluid as it goes in and actually goes out. But in this case, it was water. Regardless, you can look up the specific heat. That's what CP stands for, and water is 1. So I'd like you to do a couple calculations with that and see how that turns. Not atypical numbers for this first example. So I'm going to put half a GPM through that collector. It goes in at 70. It's a day where, given the solar conditions and the tilt and orientation of this collector, there's 200 BTH for every foot squared on this 30 square foot collector, and it comes out at 75 degrees. So go ahead and crank through it and get the efficiency. I would encourage you to pause the video and see if you can work through it yourself, and I'll be getting the answer up there. Okay, partial credit. I know I get 100 BTUs per minute is actually hitting this surface, and then the numerator I need to get the heat to the H2O, and that's easy enough to do. Now you may need to remember a couple things about it in order to do it, but we've got a 0.5 GPM, and there's about 8.3 pounds for every 0.5 GPM. So I can just line up the numbers there, 0.5 times 8.33, and then my T out minus Tn is going to be 5. All right, let's just check to see whether those calculations are going to be correct by doing the units down below. So the 0.5 is gallons per minute. The 8.33 is pounds per gallon. I neglected to put the specific heat in there, and the specific heat, the specific heat of water is 1, so I should have put it in there, but anyway, I'll get it there now. The specific heat is BTUs per pound degree Fahrenheit, and this 5 degrees is a change in temperature of 5 degrees Fahrenheit. So if we go through that, we get a lot of canceling. Gallons are gone, pounds are gone, degrees Fahrenheit is gone, and we get BTUs per minute. So we can see how much energy we actually had going into the water and take it from there. So 0.5, I'm trying it myself, times 8.33, times the specific heat of 1, times the delta T of 5, and I'm getting 20.825, or rounding it off, let's call it 21 for the collection. I'm getting 21 BTUs per minute, 2 there, and then I can go ahead and calculate the efficiency, and the efficiency is about 21%. So not very good. All right. So what could we do? Some things that we could think about. Well, maybe this collector's not positioned very well, and maybe we could somehow change things. Maybe the collector's not very good. But there's one other crucial thing that's worth thinking about that, and that is this GPM. What difference would it make if we alternate the GPM? So what we're going to do is we're going to try to change it to 1 GPM and see how it turns out. Here is a possible intuition. If I change this to 1 GPM, the water's going to be going through there faster, okay? And therefore it's going to have less time inside the collector, less time to warm up, and probably come out at a cooler temperature. Well, let me go ahead and erase this stuff and give you an number that may not be atypical, that sometimes it works out that way. Okay? It turns out that often, if our flow rate change is right at some sort of critical value, even though the water's going through there faster, we end up getting a warmer temperature going out than we did before. So again, half GPM going through that collector slowly, coming out at 75. 1 GPM going through that collector faster, coming out at 77. A little bit strange to think about, but nonetheless, that's not an unusual situation. So first of all, let's just calculate the numbers and see how it works out. QH2O. Now, hopefully we can do it in our head. Maybe pause the video and see if you can get through that efficiency all the way yourself. Okay, I got 58.3 BTUs going to the water. All right. And that's BTUs by the minute, by the way. This incident radiation was still the same, and we get an efficiency of 58%. So a tremendous improvement in efficiency just due to making this water go faster. So what's the thought behind that? Work on that in just a second. So how could that be? We have some fluid going through a tubing in a collector, and we get a certain collection rate, a certain number of BTUs per minute. And then all we do is speed up the flow, and we get a lot more collection. And what could be going on is that in going from a slow speed to a high speed, we change from laminar flow to turbulent flow, and that makes all the difference. So quick reminder on those two terms, laminar or turbulent flow. So laminar means layered, and that means that if you have some water entering a pipe, that it flows in layers. Remember that from your heat transfer, remember that we have this layer that hugs the wall that follows the no-slip condition, and that means that layer actually doesn't move. And so as a consequence, we have this layer of fluid entering, okay? And there is viscosity, which is an attractive, cohesive force, and it tends to slow the viscosity between this layer here and this layer here tends to slow this layer down a little bit and create shear. Okay, this layer here, this lower layer would be the same. Okay, and this layer in the middle is going to end up going a little bit faster so that we have a constant flow so that this flow in is balanced. But the main point is the following for heat transfer. The main point is that this layer follows a straight line path with no up and down. Layered flow, straight line path. Well, we want the heat actually to get into this fluid, gets into this fluid, and so there's heat out here from the sun. This top surface is really warm, and how is that heat going to get in? Well, it's got to get through this layer, and this layer, and we can think about how that's going to work, in particular if we contrast it with turbulent flow. So turbulent flow, the cohesive forces are not strong enough to keep that straight line path, and we end up, for any bit of water, we end up having it in general progress to the right, but have little perturbations in its flow. And it could actually end up coming up here like this and get close and then come back down here and get close. And we have progress to the right along with swirling. Well, how is that for heat transfer? And the answer is it's just great. Okay, if this top of the pipe is warm, when this water comes up here and touches that pipe, it picks up the heat and brings it and deposits in the middle. So with swirling flow, we get much, much better heat transfer. And as a consequence, just by increasing the flow rate, we can get turbulent flow. Well, increasing the flow rate involves more pumping energy. So it's something that's very, very important for us to just hit right. And it turns out that it is worth increasing the pump speed enough to get beyond laminar just into turbulent, and then after that there's not much benefit. So we want to be able to pinpoint what flow rate is right, and let's work on that and remind you guys how to do that. So what we end up doing in order to decide whether it's turbulent is, in short, we're going to compare what are called the separation forces for a fluid to the cohesive forces. So separation forces or inertial forces, excuse my arm, that's usually the way you see it in the book. I would like you to sometimes think about it as diversion forces. Are there any forces in the situation which create diversion, the possibility of water diverting quickly, and that can lead to chaotic force, chaos or turbulence. Chaos is too strong a word, but turbulent flow. And are there any cohesive forces? Well, the cohesive forces that keep water, every layer similar in path to the layer adjacent to it, is of course the fluid viscosity. And the term that is used in your heat transfer book for viscosity is a mu, and the same thing for the solar book. That's pretty universal. Okay, how about the diversion forces? Well, the diversion forces is something to work on in your mechanical engineering career, or in mechanical engineering studies. The diversion forces depend on the geometry of the situation. So we're going to come up with a way of characterizing diversion forces for this particular geometry, flow entering a pipe. And it's not that hard to figure out what's going on. It really comes from the fact that there is this no slip area. And if we have a certain flow rate coming to this point right here and then going into the pipe, it's almost like if you were looking straight on at the pipe, it's almost like you could think about there being a little band around there that water has to get in and fit through. That water has to get through that band. And so if I drew a few more lines here, excuse my fingers, so if I tried to do 5 lines right here, okay, this one's going to get in no problem. The 2 on either side are going to get in no problem, but these top ones here are going to have to divert because of that band, and so there are diversion forces. Okay, any way to quantify the diversion forces? Well, the more particles that try to get through this opening and through this band right here come to this pipe, but then have to squeeze inside this band, the more particles, the more diversion you're going to have. And that can be quantified by m dot, the mass flow rate going into the pipe. On the other hand, if the pipe diameter is bigger, there's really less of a squeeze for that m dot. So we could characterize the diversion forces as a ratio of m dot over d. You get a big m dot and a small d, you've got a lot of diversion required. You get a small m dot and a big d, no problem. There's going to be hardly any diversion at all. The likelihood of turbulence is going to be very limited. So I encourage you to think about quantifying whether there's going to be turbulence or not by comparing those two things, m dot over d and also viscosity. So that is actually, in a short, what that Reynolds did was he said, let's do a comparison of those. Let's do a ratio. And let me get that up there for you guys to think about a little bit. I don't know if you need to copy this down, but in short, what Reynolds did for various flows is he took m dot over d divided by viscosity and saw how it turned out. And then you could, for various flows, compare the result of that calculation. All right. It turns out, though, that there are a couple other constants in there. And so we might want to write this down, the Reynolds number. One way of calculating the Reynolds number for pipe flow. So a lot of times you'll see RE sub D. That means Reynolds number for pipe flow is, well, if you tried to write this as a single fraction, the D would go in the denominator. It's going to be equal to 4m dot, okay, over, there's a pi in there as well, and a mu md. Okay, so there is a really important formula. You may have emphasized another form in ME 126, but this is a really good form. And let's go through an example and see how it actually turns out. So in this example, I'll read it off and then try to get it up there. Excuse my writing in my hand. Okay, in this example, we're going to do, give me for just a second, please. We're going to do 4 gallons per minute in a 2-inch pipe. Okay, is there any way that's going to be turbulent or not? My intuition is no, but let's see how it turns out. Going to make it easy, going to convert it into SI units. So 4 gallons per minute, that is 4 times 8, that's about 32 pounds, more than that per minute, and a kilogram is about 2 pounds. So let's call that 15 kilograms per minute. That was what I said was rough, but 15 kilograms per minute is not really bad at all. And let's say if it's a 2 centimeter pipe, that's going to be a 10 centimeter ID. Okay, and of course we're going to do H2O. All right, so what I'd like you to do for starters, of course you can just plug and chug and put into this formula, but just to think about it a little bit, I'm going to do m dot over d, do that calculation, and I'm going to get the viscosity. And I encourage you to try that out and see how it works out. Hey, sorry about I gave you one bit of data incorrectly. I said a 2-inch pipe, and there's 2.5 centimeters per inch, so it should have been a 5 centimeter inner diameter. So let's take a look at how the numbers are working out. M dot O D, the likelihood that there's diversion, separation, etc., or that your heat transfer book is going to call it inertial forces. So that's 15 kilograms per minute divided by 0.05 meters. Try that on my calculator, 15 divided by 0.05. Okay, I get 300, okay, but we would like that to be, that's going to have a minute in it. We would like it to be in seconds, so I'm going to divide it by 60, and I'm getting 5, I'll write that up there for you guys, 5 kilogram meters per second. So that's m dot over d. Okay, how about the viscosity? That's nothing that we need to memorize. We just need to be good at looking the terms up. I did not do a great job on that. I didn't give you the temperature of the water, okay? And so we're going to go, in this case, with, why don't we go with 295 Kelvin water so that we can go to the tables. So sorry about that, I didn't get that earlier. Let me just remind you how that works, okay? I'm going to the tables from the heat transfer book. This is a bit earlier edition, but it should be very similar to what you got. And so you have a table like this where you have all sorts of different information, and you just need to find the right temperature. So if we're going to 295 Kelvin water, and I read across that table, I get a viscosity of 959, but that is needs to be adjusted for the exponent, and let me get that up there for you. Okay, it's 959 newtons times 10 to the negative 6 Newton seconds per meter squared. And viscosities turn out in most of our unit systems to be pretty small numbers. It's amazing that people got it that precise. In addition, it actually turns out that we think of water as viscous compared to, say, air or something like that. But man, compared to engine oil, glycerin, or honey, it's pretty low. Has pretty low on cohesive forces. Okay, let's finish it off. I think what would be helpful to do is actually take this unit and break it down. So I'm going to do that really quickly myself. Remember, a Newton second per meter squared. Remember, a Newton is a kilogram meter per second squared. So what I wrote there is a Newton, and then I need to multiply it. I still have a second in a meter squared, so I'll put that second in meter squared. And take a second to see how that's actually going to turn out yourself. How is that unit combination going to turn out? Okay, and again, if you look at it, you should see that I'm going to get a kilogram per meter second. So let me write that up there. And man, I am being a little bit sloppy today. I did a poor job over here. This is a kilogram per minute per meter, and then we made it into seconds. So this should have been a kilogram per meter second. Okay? And so one of the main points I wanted to remind you guys of with the Reynolds number, if we end up taking this m dot and dividing it by this mu, we're going to get all the units to work out, to drop out. And the Reynolds number is unitless. It's a comparison of forces. Okay, let's put it together and see how that all turns out. So I've got my m dot over d, that's that 5, and I've got this viscosity. So I'm going to do 5 divided by 959 times 10 to the negative 6th. Okay, and then I need that 4 in there. I didn't have that 4 in there, times 4. And I'm going to divide by my pi. Okay, and I'm getting a little bit over 6,000. So the Reynolds number in this case, trying to sum it up for us, the Reynolds number is 6,638, unitless. Okay, so what does that end up telling us? Well, that ends up telling us for every different type of flow around a cylinder, flow over a plate, flow through a pipe, like this scenario right here, there is a break-off number that tells us whether we're in the smooth region or the laminar region, and that works for any type of fluid. It's a very interesting thing that we can come up with a calculation for a geometrical situation that will tell us whether it's laminar or turbulent, whether we're doing carbon dioxide, water, air, honey, glycerin, etc. And the cutoff we usually have is below 2,100 is laminar, above 4,000 is turbulent, in between is termed transitional. So we definitely got turbulent flow in this case. And we might even be able to lower the mass flow rate some in order to get turbulence. All right, so what we're working towards is understanding efficiency of flat plate collectors, and a huge part of it is whether the flow that we get through the tubing is turbulent or not, and you guys can do that calculation. I'd like to do just a little bit more where we figure out the H value, but to finish off for today, let's get that other version of the Reynolds number flow up there. So this is a good, valid form of the Reynolds number. To me, it conveys a lot about tube flow. The other form comes from the fact that in many scenarios, we actually figure out the Reynolds number by thinking about the average speed of a fluid. So that can easily be incorporated into this. So a quick reminder how that works. If you have a fluid with speed V, average V, going through a pipe with cross-sectional area A, the volume flow rate can be gotten by doing that speed times the cross-sectional area. I mean, just taking a numerical example that you don't need to write down. If a fluid's going 4 feet per second and it's going through an opening that is 2 feet squared, we're going to get a volume flow rate of 8 cubic feet per second going through that pipe. All right, how do we turn that 8 cubic feet per second into a mass flow rate? Well, we would multiply by the density. So there is one very basic relationship that you have in a pipe flow or duct flow, is that the mass flow rate is the density of the fluid times the average speed of the fluid. It's really important that the average speed in cross-sectional area. Okay, so what we want to do, there's a form of the Reynolds number that just has speed in it. What we're going to do is we're going to take this and put that in there and see if we can simplify it. And I encourage you to do it yourself. If you're in heat transfer, it might be a valuable exercise to remind yourself how this works. Okay, so there is the first step, and that would be a good formula so that you could write down on your note card. But many of you know it ends up being simpler than that. And in the particular case where we're doing flow through a pipe that has a circular cross-sectional area, we can replace that area. So the area of this opening through which the water is going is pi d squared over 4. That's the same as pi r squared, but usually this is expressed in terms of the diameter. So let's keep going. Okay, it's going to get a little bit messy and then a lot simpler. Okay, so what can we get rid of? We can get rid of the pi's, we can get rid of the 4's, and we can get rid of 1d. So let's see if I got it. So just see if we can finish that off. The Reynolds number. Let's see, I definitely need a rho in there. Okay, I definitely need a v, and then I need a d, and I'm dividing by the viscosity. So there is your other form of the Reynolds number that you're used to using. In addition, there is one final form on that that is very useful. So let's get that up there because it can pay off to know this other form. And that is the following, okay? If we end up taking this rho and move it to the denominator, we end up getting v times d divided by mu over rho. Okay, and mu over rho is a really important idea in fluid flow and heat transfer, that combination. So let me just try to describe that for you guys really quickly, okay? What if we had a fluid that's going through a pipe and we wanted it to be laminar? What would we want mu to be like and rho to be like? Okay, given that it was a certain volume flow rate, let's say like we're trying to do 4 gallons per minute, okay? And that 4 gallons per minute could be honey, it could be water, it could be air. A gallon's a unit of volume. Okay, first of all, what would we want rho to be? Would we want rho to be large or small? And it turns out we want density, we want this fluid not to be very dense. What's going on? We're trying to squeeze that water into that area and deal with that no-slip condition at the perimeter, so we would want the density to end up being very low. Okay, how about the viscosity? We'd want the viscosity to be very large. So it turns out that what we'd want is to prevent turbulence, we would like a large mu and a small rho. So it turns out that this factor here, mu over rho, is actually, in a sense, tells us for a fluid how unlikely it is that the fluid is going to be turbulent. So the bigger mu over rho is, the more likely it's going to be laminar. And so as a consequence, that combination has been combined into a single property for a fluid, which is called the kinematic viscosity. And it is indicated by a Greek symbol, which is a nu. It kind of looks a little bit like a V. And for the last thing for today, then, we can write the Reynolds number as V times speed, average speed times diameter, divided by the kinematic viscosity. And so we end up having 3 different Reynolds numbers, which are all equivalent. Let me get that up there. Okay, and so sorry about my moving the board. That is our third formula of the Reynolds number. All right, to finish off class, let's just verify that it works out, this new formula works out. And then guys can keep working your way, you can keep working your way through homework number 8. Problem 1 is to finish off that spreadsheet, and there's a lot of good work about solar, just going through that spreadsheet, thinking about what the terms mean, getting the graphs, getting the total solar, and thinking about the results. The next problem, couple problems, get you going on collector efficiency, and then also starting to think about Reynolds numbers and then Nusselt numbers. So you can make some progress on that. Next lecture, we'll start getting on the Nusselt number. But to finish things off, if we had the information like this, how about calculating the Reynolds number using this formula right here? Well, D we got, so that's easy enough. Kinematic viscosity. Once again, we would go to our tables, and I'm going to try to use the same line there, 295K. They have kinematic viscosity, in there, and give me just a second to get that value for you guys really quickly. Hey, actually, I'm sorry, the heat transfer book doesn't give kinematic viscosities in their tables. But there are many tables that have it in there because it's such a useful parameter. So here's a good approximation of the kinematic viscosity of water. 1 times 10 to the negative 6 meters squared per second. All right, hey, let's do that calculation. We'll calculate the Reynolds number this way. So we got diameter, we got viscosity, we need speed. So for speed, we're going to use that m dot equals rho VA formula, something that eventually just gets tattooed on your brain, and we're going to solve that for speed. So the average speed of the water in this situation is going to be equal to m dot divided by the density divided by the cross-sectional area. Okay, so 15 kilograms per minute, that's 0.25 kilograms per second. Okay, density, I'm going to use a rough and ready number for water. 1,000 kilograms per meter cubed is a really good number. Of course, it varies somewhat with temperature, but we're going to get pretty darn close using that. Okay, and then how about cross-sectional area? Okay, well then for that we're going to use pi, and then we're also going to do 0.05, the diameter squared, which is 0.05 squared. Sorry about my writing, it's a little bit small over there. All divided by 4. So good exercise. Let's see how that speed turns out, and think about whether that really makes any sense. So I'm trying it myself on the calculator really quickly. I encourage you to do the same. So 0.25 divided by 1,000 divided by pi. Okay, and then I got to divide by 0.05 squared. That 4 comes up to the numerator. And I get about 12.7 centimeters per second. So, that's 2.5 centimeters is about an inch. So 5 inches per second, so 1/1000. So that water's not moving that fast. My inclination would be to say, hey, look, it's probably going to be laminar, but let me get that up there. 0.1273 meters per second. Okay, and now we've got it all. So the Reynolds number, last calculation of the day, is going to be the speed, 0.1273 meters per second, times the diameter, 0.05 meters. And then how about water's resistance to becoming turbulent? It's mu over rho. Well, it's an incredibly small number. It's 1 times 10 to the negative 6 meters squared per second. I mean, that might be an interesting thing to do at some point, is to compare that kinematic viscosity to that of carbon dioxide, and you might be surprised that carbon dioxide turns out to have more resistance to turbulence in polite flow than water. In any case, the point of today, though, is to crank through that and see how that turns out. So speed times diameter, 0.05, divided by kinematic viscosity. Okay, and I get about 6.366. It's not exactly the same as the number earlier, but I was being a little bit rough with some of my numbers. It's basically very close to the same. If I'd been more precise, I would have gotten the exact same answer. But nonetheless, I get the same conclusion. It's turbulent. Now I can get to work and get the H value and assess how that's going to work out. So that's it for today. As I mentioned earlier, I encourage you to get going on Chapter 8. A lot of good work trying just to get to that Excel spreadsheet and understand what's going on, and doing that problem on the homework number 8 that requires you to think about collector efficiency. So more next week. Please feel free to email me if you have any questions. Have a great weekend.
Hi Bridget, happy birthday. Sorry we can't celebrate with you at school. Hope you're doing well. Bye.